Have you ever gazed upon the night sky and pondered the mysteries of the universe? A question as old as humanity itself, and yet it never ceases to captivate our curiosity. The universe, in all its grandeur, is a cosmic stage filled with celestial wonders. This vast expanse that stretches out to infinity is our observable universe. It's a cosmic sea teeming with an estimated 2 trillion galaxies. Each of these galaxies, a swirling kaleidoscope of stars, gas, and dust. And within these galaxies, it's estimated that there could be up to 1 septillion stars. That's a 1 followed by 24 zeros, a number so enormous it's nearly impossible to comprehend. But the universe is not just a showcase of astronomical numbers and celestial bodies. It's a grand tapestry woven by the fundamental forces of nature. These forces, like invisible puppeteers, orchestrate the dance of galaxies, the birth and death of stars, and even the structure of matter itself. The 4 fundamental forces of nature are gravity, electromagnetism, and the strong and weak nuclear forces. Each plays a crucial role in the cosmic symphony. Gravity, the master of the macroscopic, governs the motion of celestial bodies. Electromagnetism lights up the universe, defining interactions between charged particles. The strong nuclear force binds the atomic nucleus, while the weak nuclear force mediates radioactive decay. For centuries we've probed these forces, seeking to unlock the secrets they hold. From Newton's apple to Einstein's relativity, our understanding has grown, but it has also deepened the mystery. How do these forces interplay? What ties them together? And can we find a single theory that elegantly explains them all? These questions sparked a quest, a journey that would take us beyond the celestial bodies and into the world of the infinitesimally small. Here in the realm of quarks and leptons we hope to find the answers. Our journey to understand these forces has taken us from the vastness of the cosmos to the tiniest particles of matter. A journey that brings us to the doorstep of a theory as elusive as it is intriguing, the string theory. Our understanding of the universe has evolved from contemplating the celestial bodies to examining the minuscule particles that make up everything around us. We've always been fascinated by the cosmos, gazing at the stars and pondering the mysteries that lie beyond our terrestrial home. Our early ancestors mapped the stars, constructing elaborate calendars and navigating vast oceans guided by celestial bodies. Over time, we've developed telescopes, allowing us to peer deeper into the cosmos, discovering galaxies far, far away, and even understanding that our own Milky Way is but one of countless galaxies in an ever-expanding universe. Yet, as we looked outward to the cosmos, we also began to look inward, to the very building blocks that make up the universe. We discovered atoms, the basic units of matter, tiny particles so small that millions of them could fit on the head of a pin. But we didn't stop there. We delved even deeper, discovering that atoms themselves are composed of even smaller particles, protons, neutrons, and electrons. From there, our journey took us into the strange and often counterintuitive world of quantum physics. Here, particles can be in 2 places at the same time, and they can even pop in and out of existence. It's a realm where the laws of physics as we know them seem to break down, replaced by a new set of rules that are as fascinating as they are perplexing. One such rule is Heisenberg's uncertainty principle. It tells us that we can't know both the position and velocity of a particle at the same time. The more precisely we measure one, the less precisely we can know the other. It's a principle that challenges our everyday experience and understanding, yet it's fundamental to the behavior of the quantum world. As we journey from the macro to the micro, from galaxies to atoms, we find ourselves on the brink of a new frontier. Now we delve into the quantum realm, where the fabric of reality itself is woven. Welcome to the quantum realm, where the rules of classical physics don't apply. Here we're dealing with the smallest particles in the universe, where the seemingly impossible becomes the norm. To make sense of this, scientists developed quantum field theory, or QFT for short. But what is QFT, you may ask? Well, it's a bit like the ocean. Imagine the ocean as a field stretching out in every direction. The waves you see are excitations or disturbances in that field. Similarly, QFT suggests that all of space is filled with fields, and the particles we see are excitations in these fields. So an electron isn't just a tiny point in space. Instead, it's an excitation in the electron field that extends throughout the universe. This might seem strange, but it's this concept that allows us to understand the world of the very small. QFT successfully describes 3 of the 4 fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. Electromagnetism is the force behind light and electricity. The strong nuclear force holds atomic nuclei together, while the weak nuclear force is responsible for radioactive decay. But there's one force that QFT struggles with: gravity. Gravity, as described by Einstein's general relativity, is a result of the curvature of spacetime caused by mass and energy, but in the quantum realm, this doesn't quite fit. The smooth curvature of spacetime clashes with the inherent jitteriness of quantum mechanics. This discrepancy is one of the biggest unsolved problems in physics. As we delve deeper into the quantum realm, we find that our understanding of reality becomes less certain. The familiar solid world dissolves into a sea of fields and particles popping in and out of existence. It's mind-bending, it's fascinating, and it's just the beginning. But one force eludes this elegant theory: gravity. Could there be a theory that unites them all? As we move forward, we'll explore the intriguing possibility of a theory that could reconcile gravity with quantum mechanics. Welcome to the enigmatic world of string theory. Enter string theory, a bold attempt to harmonize the symphony of the cosmos. Picture a universe not made of tiny particles like dust in the wind, but a cosmic orchestra of tiny vibrating strings of energy. This is the premise of string theory, a theoretical framework that seeks to reconcile the seemingly incompatible worlds of quantum physics and gravity. In the traditional understanding of physics, the smallest fundamental particles are points. But string theory proposes a radical idea. These particles are not points, but tiny loops or strings of energy. And just as a violin string can vibrate at different frequencies to produce various notes, these strings of energy vibrate to create different particles. The electron, the quark, the photon, all are simply different notes in this cosmic symphony. But the music doesn't stop there. String theory also suggests the existence of multiple dimensions, far beyond the 3 dimensions of space and 1 dimension of time we are familiar with. Imagine a symphony, not limited to the notes we can hear, but one that reverberates across dimensions we can't perceive. Yet the melody of string theory is not without its discordant notes. The theory is challenging to test empirically, as the strings it proposes are so minuscule, about 100 billion times smaller than a proton. This places the experimental verification of string theory beyond our current technological capabilities. Moreover, the mathematics behind string theory is incredibly complex, requiring a deep understanding of advanced concepts such as supersymmetry and extra dimensions. The theory's beauty and elegance are locked behind these mathematical intricacies, making it inaccessible to many. Yet, string theory remains a theory, its beauty and potential locked behind mathematical complexity and lack of empirical evidence. Despite these challenges, string theory continues to captivate scientists and laymen alike, promising a harmonious symphony of the cosmos that could forever change our understanding of the universe. String theory, while fascinating, is not without its challenges and criticisms. This ambitious theory, aiming to reconcile our understanding of the microscopic and macroscopic world, faces hurdles that are not easily overcome. One major challenge is the scale at which these strings are said to exist. These hypothetical strings are believed to be so incredibly small that they're beyond the reach of any current technology. They operate at the Planck length, a scale where a millimeter is to the observable universe what a Planck length is to a millimeter. This makes direct empirical testing of string theory a daunting task, to say the least. Additionally, the energy required to probe these strings is astronomical. To put it into perspective, it's estimated that a particle accelerator large enough to test string theory would need to be roughly the size of our galaxy. That's quite a bit larger than the Large Hadron Collider, currently the world's most powerful particle accelerator, which sits at a mere 17 miles in circumference. But it's not all doom and gloom for string theory. Despite these challenges, the theory has stirred considerable debate within the scientific community, sparking a continuous quest for new ideas and approaches. This is where the value of string theory truly shines. It pushes the boundaries of our understanding, prompting us to question, to probe, and to wonder. It encourages us to look beyond the known and venture into the realm of the unknown. It inspires us to imagine a world where all the forces of nature can be explained under a single, unifying framework. While string theory may not provide all the answers, it certainly drives the conversation forward. It compels us to rethink our understanding of the universe, pushing us ever closer to the ultimate goal, a complete theory of everything. While we may not yet have the keys to unlock all the secrets of the universe, the pursuit of knowledge, like the universe itself, is infinite.